Problem 3. A bear spies some honey and takes off, starting from rest, accelerating at a rate of 2 meters per second squared. If the honey is 10 meters away, how fast will his snout be going at the instant he reaches the honey? In other words, what's the final velocity? And how much time will it take to reach the honey? And then draw a velocity versus time graph. Okay, so let's put number 3 given. Well, here's your campsite, and here's your jar of honey. It's very important that you draw these things, perfectly. Your jar of honey, just like the Winnie the Pooh jug, okay? And then here's the bear. I don't know if my bear is going to be very good. No, that's a terrible bear. It looks more like a porcupine or something. It's got ears. Actually, it's a great big old huge rat. All right, so there's our bear. Give him a little tail. All right, and he sees that honey, starts taking off. So the initial velocity, if you read the problem, the bear starts from rest. Now that's a big clue. In these problems, it's not going to say the final velocity or the initial velocity. It's going to be disguised a little bit. You have to figure it out. Oh, starts from rest. That means the starting velocity is 0. So here's the bear. I'll just draw the bear as another blob with legs. Okay, and the bear is just reaching the honey, so we want to know what the final velocity is. We don't know what it is. But we do know the displacement. It says the honey is 10 meters away. Well, that's our displacement. That's how much the bear is going to change its position. And we know that the bear accelerated.
Wait, how do you know it's 10 meters?
Because it says in the problem, the honey is 10 meters away when the bear started.
I know.
Well, displacement is how much you have to change how much you're going to change your position. So your bear started here, it's going to move 10 meters to get to the honey. And I can show that as like this. This is how far the bear is going to go. Okay? And then we know the acceleration is given as being 2 meters per second squared. So we're given the acceleration. What are we trying to find? A. How fast will the snout be going at the instant he reaches the honey? Well, that's the final velocity. And then B, how much time will it take to reach the honey? And C is the velocity versus time graph. And then we're going to solve. Now, if you do this correctly, the rest of the problem goes so much faster. So let's do part A. Well, what do we know? We know the initial velocity and the displacement and the acceleration. I'm trying to find the final velocity. What am I not yet given and I'm not trying to find yet? Time. No time given. No time needed. Which one has no next to time? The fourth one on the list. Okay, so write that one down. And then start looking at what's given. First of all, it says V naught is equal to 0. So what's 0 times 0? 0. That term goes away. So v squared is equal to twice. The acceleration is 2 meters per second squared. And then what is delta x? 10 meters. And so now v squared is equal to 2 times 2 times 10 is 40. And then what do we get for units? Meter, what's meters times meters? Per second squared. Now I don't want v squared. What do I want? I want v. I want the final velocity, so I have to take the square root of both sides, including the number and the units. So v equals, well, I think the square root of 40, I'm not a human calculator, I just remember from this morning. I believe it's 6.32 if you round it off. And what's the square root of meters squared per second squared? Yeah, it's meters per second, which it darn well should be. And there's my answer. What's that? No, I don't want you to leave it in radical form. If you wrote like 2 root 10 or that implies infinite precision in your answer. And remember, these are all based on measurements, and measurements are not perfect. They all have a certain level of uncertainty to them, and you don't want to reflect infinite precision in an answer that's based on uncertain measurements. So you just round it off, usually 2 or 3 significant figures.
Okay.
Now, if I was going to get really technical, this only has 1 significant figure, and so does this, so you should round that to 6 meters per second. But I'm going to say, hey, 2.00, 10.0, like 3 significant figures. This is okay. All right, let's do part B. We want to solve for time. Now, I could use this final velocity if I wanted to. But what if I made a mistake? I don't want to carry that mistake into part B. So I don't want to use final velocity. What doesn't have final velocity in it? Equation number 3, which is our displacement is equal to our initial velocity times time plus 1/2 the acceleration times time squared. And we want to solve this for time. Now, if I gave you a non-zero initial velocity, you would have to use the quadratic formula to solve for time. But happily, what's true about the initial velocity? It's 0. So no matter what time is, this thing goes away. So delta x equals 1/2 a t squared if you start from rest. And now we're going to solve for time. I'm going to multiply both sides by 2. So 2 delta x equals, and then I'm going to divide both sides by the acceleration, equals t squared. So t is going to be equal to the square root of 2 delta x over a. And now I just need to plug in my values. So the 2 cancels the 2. So the square root of 10, what is the square root of 10? Like 3 point something? It's 3 point something. Somebody help me out. I don't have a calculator up here. 3.17? 16? So we'll say t is equal to 3.16. Now what units should we get? What units does time have? Seconds. Is that what I get when I do this? It actually is. This is meters divided by meters per second squared. So what do? You reciprocate and multiply. So that's times second squared over meters. The meters cancel. I get seconds squared, but I'm taking the square root of it. So I get seconds. Woohoo! Now I can do part C, which is to draw the velocity versus time graph. So here's velocity, here's time. 1, 2, 3. I don't need to go to 4. 1, 2, 3, 4. Time in seconds. Now what's my maximum velocity? It's going to be 6.3. So I'll go 1, 2, 3, 4, 5, 6. So 2, 4, 6. This is velocity meters per second. Okay, and then we're starting from rest. And then at 3.16, which is less than 3.2, somewhere in here, we're going to go 6.32. So that would be about right here. And there's the velocity versus time graph for that bear. So let's look at the whole problem here. Notice that I didn't copy down the problem. I just used given, find, and solve with a picture. Draw what's given around your picture. That really helps. If you can visualize and understand what the heck's going on, you're going to be able to solve the problem quickly. If you can't do this, you're just going to be thrashing around with equations, which is not what we want. Then we figured out what we're trying to find. We went through using the kinematic equations for part A and B, and then just using what we got to draw the graph. Question?
So we have to memorize those 4 equations?
The question was, do you have to memorize the 4 equations? No. What you may do is create an equation list for the exam. And you're allowed, so you'll be allowed to have that. If you write that down on a sheet of paper, you'll be able to use it during the test.
Okay.
But you know what? You're going to use these so much that you're going to have them memorized by the end of the unit.
Okay.
Or at least by the end of, a couple more units. All right, that's all.